Liquid ice. Online lessons.
Good morning, everyone. We welcome you at the online lesson realized within the Liquid Ice project. And we will start with a short introduction to the day we are celebrating today. Let me just start my presentation to introduce the International Day of Women and Girls in Science. This International Day started in 2016, so exactly 10 years ago. And why do we need such a day? It was proclaimed by the United Nations, and it promotes full and equal access to and participation of women in so-called STEM. STEM comes from science, technology, engineering, and mathematics. And as it was checked in 2016, even though we have theoretically equal chances, less than 35% of STEM graduates, so the people that go to the studies dedicated to this science, technology, engineering, and mathematics, and finish it successfully are women. If we look for engineering and IT branches, it's even less. It's not more than 15% of graduates. Therefore, United Nations thought that it's good to promote participation of girls and women in science. And today we will bring you to polar regions. And in polar regions, it's not only because of science, but it's also because of harsh conditions. And therefore, for many years, at least in our Polish polar station Hornsund, that our Institute of Geophysics is taking care of, we had mainly male wintering teams. And it was Danuta Bednarek, the first woman who was wintering, so spending the whole year at the station, and it was in 1995. And next woman who was wintering in at the station was after 11 years. At the moment, since 2008, we have been observing regular women wintering at the station, and it's totally normal for us that we have 2-3 women in each group of around 8-10 participants of the wintering team. If you would like to get some more information about Antarctic and Arctic women, I encourage you to read the book if you are from Poland, and you may read in Polish the book by Dagmara Bożek. She has also a project and a website available also in English, and documentary video, which is in Polish but with English subtitles. And here I will share with you a short trailer of this video to encourage you to watch it. And meanwhile, I will send you the link to this video on chat. And now I introduce Dr. Ekaterina Rets. She's an assistant professor at the Institute of Geophysics, and she's been studying how changing climate affects hydrological systems from glaciers and snow to rivers. She's involved in this topic more than 16 years now, and she also has a vast fieldwork experience traveling to Svalbard, Caucasus, Tian Shan, Siberia, Altai, and Kamchatka. And from the scientific perspective, I think a very important achievement is that she was the contributing author to the IPCC 6 assessment report. IPCC is a special intergovernmental panel dedicated to climate change and to science behind climate change. Okay. Katia, the floor is yours. I will stop sharing now and give you the floor. And meanwhile, I will also send on chat the list of attendance, and please fill it with the information about the number of students that are together with us today.
Hello, everyone. Thank you, Agata, for the introduction. Um, I guess most of you have heard about the thing that climate is changing. And the majority of you probably also have heard that glaciers are melting. But not everyone are sure that why we need to bother about that glaciers are melting, and what are the consequences if they're important. Why do we need to be bothered about that at all? So as Agata has said, I've been studying rivers and glaciers and snow for more than 16 years, and trying to figure out how climate change affected processes happening with these natural systems. Um, since I've been in school, I like to be outside in the nature a lot. And at some point, I decided that I need to choose a profession where I will be able to travel all my life. So that's how I ended up in geographical faculty. And this is how my life looked during last almost 2 decades, traveling all around the world, mostly in mountains in Arctic, because I was mesmerized by mountains at some point when I was studying. Settling observations and doing experiments in mountainous and remote regions, from Kamchatka to Svalbard, Altai, Siberia, Tian Shan, and many other reasons. Of course, the life of scientists and environmental scientists not only consists of field research, it's only one small part of our work. And being a scientist is, I would say, it's close to running a small enterprise, because you do all the cycle from finding funding, like fundraising, then you do your field research. Of course, your field research is never enough to do some vast generalizations and studies for huger regions, for huger time spans. That's why you also need to collect and analyze observational data from state agencies. And then we also use a lot satellite remote sensing data, of course, because it gives very extremely valuable information about like larger territories, and provide us possibility to do bigger generalizations. And with this old data, you need to analyze it. Quite often, you construct models of those processes that then you study, and after that, you need to get to some conclusions, and you put these conclusions into scientific papers. And also important part is reports, those reports that go to on the tables of policymakers and actually affect what is going on in our world and trying to change things. One of the most famous and important reports in this sphere in climate change is that one that Agata has already mentioned, is Intergovernmental Panel on Climate Change, IPCC reports. And I had the chance to participate as contributing author to this last report, and the things that I will be telling you today, they are will be partly based on this huge work that is, in fact, summarizing the most important, the most impactful research of last decades, and drawing those conclusions that most of scientists around the world are most confident in and agree the most between each other. And also I'll show some of the results from the Liquid Ice project. It's a huge European project that's being coordinated by our Institute of Geophysics, Polish Academy of Sciences. And I also take part in this research, and I'll show you also some things from our project. So let's start from what glacier is. By the definition, glacier is ice of natural source flowing, flowing because of the force of gravity. Every glacier consists of two parts. The first part, upper one, is called accumulation zone, it is where the ice is generated. How ice is generated? When the snow when the seasonal snow falls in certain territory and it doesn't melt out during the winter, during summer, I'm sorry, then the next year it becomes firm. So it's a bit more dense snow. Then it becomes more and more dense. Some recrystallization processes happen with that, and then it becomes ice. And this ice, it acts as liquid, actually, not but liquids, not as water, more like a jam. So if you put a drop of a jam on a glass, for example, it will start flowing down very slowly. That is how ice actually acts. So this ice starts flowing down by the force of gravity, and then it gets to those areas that is called ablation zone. In this area, climatically, the ice couldn't have been formed, but it just happened to get here because ice flows. And in this area, glaciers melt always in any climate. So when you hear that glaciers are melting, actually it's true in any climate. In cold climate, in warm climate, glaciers will be melting in this ablation zone. But the question is whether their position and the glaciers are in balance with current climate, or the climate is changing, then the glacier starts changing as well. So if climate becomes warmer, then this accumulation zone, it shrinks to the higher elevations, and less ice is formed, and then ablation zone also shrinks, and the front of the glacier moves upper. And if the climate becomes colder and more humid, then we get more snow, more ice, and the glacier moves forward. During those periods when the glacier is in the balance with climate for quite a long period, then this certain form of landscape is formed that is called moraine ridge. Frontal moraine ridge or end moraine ridge. How is it formed? You see there are like lots of rocks around glacier, and lots of mountains and rocks are falling on the surface of the ice, and ice, while slowly moving, it drags those stones till its front, and then after that they are just settled there because they can't move any forward, and nothing is moving them. So this and marine ridges, they actually mark those periods when glaciers have been stable in one stable position for a long time. And we can date them using some specific methods. I won't go into details, but we can date, using this method, we can estimate where the glacier was very long ago, where no photos existed. Right now we can use photos, for example, to see the change on the glacier front, but for the previous periods we can date these end moraine ridges. Using this method, we can estimate then all over the world the glaciers have been moving back to the upper elevations ever since mid-16th century. But of course, this only gives us an idea that the glaciers has been shrinking, but we don't know exactly how much ice loss has been, ice mass has been lost. Since mid-20th century, special observations on glaciers began using glaciological method of glacier mass changes measurements. It takes actually, like roughly speaking, measuring how many snow was deposited this year, and then how much snow and ice has melted during the summer. So then you calculate a simple balance, and you see if you have positive annual balance or the negative annual balance. It sounds quite easy, but it's only easy in theory. In practice, as those measurements take place in very harsh climate conditions, often in Arctic, and that this is how it looks in reality. So like digging snow pits, is huge well in the snow. It is very, very labor intense and it's difficult and complicated. That's why there are only 60 glaciers, around 60 glaciers all around the globe, with more than 30 years of ongoing glaciological mass balance measurements all around the world. Of course, it's not sufficient enough to draw any huge generalization. That's why we also use satellite observations. Also, roughly speaking, you have two images of Earth's surface. One, for example, first image is 2014, and then the second image in 2015. You can estimate elevation of the surface during in the of this year and then of that year, and then just see the difference. Changes in surface elevation. That is also how you can derive changes in glacier mass. This method is not that accurate as the previous one, and we use this one as like a golden standard to calibrate and validate this method, but still it works pretty good. With snow, it's much more complicated. Why? Because snow has very different density. What does it mean? It means how much water we get if we melt a bucket of snow. The snow density can vary from 100 to 600 kilograms per cubic meter. So that means from the bucket of snow, we either get like 1/10 of it or more than half. And snow density is very difficult to measure from the space. In fields, in reality, how do you measure snow density? You weight with a certain special scales the snow layer by layer. This is how you derive density. It also changes during a whole year from deposition to snow melt. And if from space it's relatively there are relatively accurate methods to measure snow depths, and snow cover extent is also quite easily seen. It's very difficult to measure snow density, and it can vary to a great extent. So that is the problem that is not solved and even not close to be solved. So probably one of you can solve it someday. But anyway, if we see how the mass of glaciers has changed using these both methods, the glaciers have been losing ice mass ever since mid-20th century. And during last years, this ice loss has increased and intensified a lot. For example, in this study, last huge, most comprehensive study on the subject, they've shown that in last roughly 10 years, the rate of mass loss has increased by almost 40% compared to previous 10 years. So every 10 years have huge acceleration. Right now, global glaciers mass loss is estimated at 273 gigatons per year. So how big is 273 gigatons? Because like, number that you can't grasp. You can either try to imagine 50,000 Cheops pyramids. That is how much ice we lose every year around the globe. And that is 30% more than, I'm sorry, 30%, of course, not 30 times, than total annual runoff volume of Danube River. Also, you can try to imagine those of you who have been closer to lower reaches of Danube River. And if climate change will go on with those rates that we anticipate, in some regions around the globe, for example, in Europe, basically in Alps, in Caucasus Mountains, in New Zealand, North America, Scandinavia, glaciers will be almost gone by the end of the century. And we will, in some regions like Central Asia, where there are lots of glaciers, only 20% of those glaciers will still be there. And only in Arctic, we will still have half of this glacier mass that we used to have. With snow cover, it's a bit more complicated because there is a huge spread between estimations due to uncertainties in estimation of snow density. But the general trends, estimated trends are almost the same. So we have decrease in snow cover thickness and snow cover water equivalent in spring and winter months, so it's close to maximum snow cover extent in those regions that are marked red here. So it's true for Europe, Central Asia, part of Eurasia, and part of North America. So in most regions, we actually see a decrease in snow cover. So what are the consequences of these processes? Snow and glacier degradation actually propagates through all environmental system, causing very and through environmental systems to our like water taps in our homes. And all those processes are very much interconnected, very complicated, and not studied enough. So there's like still huge field to study what's going actually, what are real consequences of these processes. But if we draw a very simplified scheme, the main two groups of consequences are changes in water, in the release of the water from glacier and snow melt, the amount of this water and the timing when we get this water, and changes in land surface where the glaciers used to be. Glaciers retreat, they leave different surface, and snow cover used to be present during whole winter, and now it's present during some sporadic times, and it also changes land surface. And these are one of the main consequences is changes in water ability for different types of water use, from drinking water, crops production, hydropower production, and others. Floods, of course, droughts, wildfires, landslides, and glacier lake outbreak floods. It's also an interesting process because on the end of the glaciers, when they're retreating, often a lake is formed on this moraine dam, moraine ridge, and then this ridge can break quite often, also because it consists partly of ice. It also melts, and then very devastating floods appear that I've observed consequences of these floods, and like it's really scary. So in terms of water amount, and of course we won't go through all of these processes because we don't have much time, and that's a topic for a course of lectures. I'll just tell you a bit about water availability aspect, I think, because it's like one of the most evident things. So from the perspective of water availability, when the glacier and snow become glaciers, first of all, in this context, become to melt with bigger intensity, first we have increase in water availability. So more water is released from the glaciers. And here there are problems with increase of amount of water, with floods. Then some peak water moment, we reach some peak water moment, after which decrease in the area of glacier can't compensate for the increase in melt intensity anymore. So the climate becomes even warmer, but there's less ice available to melt. So the amount of water starts decreasing. And then at some point when glacier disappears, there will be no more glacier runoff. Where we are at this graph now. So in quite a lot of regions around the globe, we are already past this peak water moment. So we have already diminishing glacier runoff. That is all these red and orange dots. That is North America, South America, almost all Europe, North Caucasus. So actually, it's easier to say where we have still a rising amount of runoff. It's in high mountains of Asia region, but it also will pass in the mid-century. It's not not very. It's not very long left to this moment. And what will happen with river runoff? This estimation, it's all already quite long ago, but it's the most comprehensive estimation and projection of how runoff of rivers will change because of this glaciation. So these authors have found that even on rivers with only 2% of their watershed covered with glaciers, like very, very small fraction, we will see increase by at least 10%, but it can be 20, 40, 60% by the mid of the century or the end of the century. That sounds not very dramatic, like 10%. Probably we can save some water and don't care much, but that is on average level. And see here, you can see an example how the share of glacier runoff looks in an average year. This dark blue sectors compared to light blue, that is precipitation in high mountains of Asia region, and that is how it looks in a dry year. So during dry years, glacier runoff in most of this territory is gives at least half of freshwater resources and sometimes more, and that is equivalent to critical needs of more than 250 million people. So that's like a huge amount of population. So you can imagine if we glaciers melt out, 250 million people will receive zero water this year. So, and that is already pretty much catastrophic. And with changes in also in other surrounding terrain, increase in dryness of climate, in aridness, and increase in water usage and changes in population. There also is expected an increase in dependency of the lowland population of the mountain river runoff. So mountain river runoff will decrease, but dependency on this mountain runoff will increase by the end of the century. And more than 25% of world population will critically depend on the source by mid of 21st century, by 2050 or something like that. How will it spread all around the globe? So red territories are the most critical ones. It's high mountains of Asia region, China, Middle East, also some regions in Europe, red and yellow one. So that would be the problem that would touch, that would border almost majority of regions around the globe. And it's not only between the years, and for example, for some regions, here on this photo, you can see that North Caucasus region is characterized by less role of glacier runoff. But still, in this study, we've shown that for some summer months of the year, if the glaciers melt out, new low flow periods will appear when the runoff will diminish by 50–90% during several weeks, during 1 month, and that would create critical bottlenecks that would make lots of problems for local water managers. What to do with wastewaters during these months where they used to have lots of water and now they have no water. How to distribute this runoff within the year, whether we need to construct new water dams, etc., etc. So quite a lot of pressure on economics and on water management, even on those territories where this glacier runoff is characterized as supportive source. With snow cover, also we see that is like a small preview on the study that we are doing in Liquid Ice project for Norway. and for Norway hydropower plants and hydropower production is that earlier melting of snow brings lower spring flood, and that brings disruption in water reservoir management. So we see that these consequences in changes in snow and glacier cover, they are very complicated and sometimes not that visible before you dig like deep inside of these processes and see not only how total amount of water changes, but when it changes, where, during what season, during what time, and etc., etc. So there are quite a lot of other aspects that are still unknown and need to be studied. So I think I will end here, and some takeaway messages that I wanted you to remember from today's election is that glacier and snow are natural reservoirs of water, and degradation of these natural reservoirs they bring a wide spectrum of consequences. From the most obvious is changes in water resources availability to increase in natural disasters such as floods, droughts, landslides, glacial lake outbursts, and wildfires, and many others. And it's not only important how much water we will be lacking, but also when and where, and those critical bottlenecks that will appear in different spheres of water management when we that are already appearing, and that would be even more important in future climate. And that dependency rate of world population on snow and glacier water from mountains is expected to grow dramatically. So this we will get less water, but we will need it more than before. So it's like a doubled effect. So that would be the end of my story. But what I also wanted to tell you and to encourage you is to choose those paths that you like, and I wanted to show you that there are lots of things that are not studied, and we need young brain and young forces in moving it forward. And I really believe that your generation, with availability with new tools and like artificial intelligence and availability of all possible information around the globe, will be much better than ours in this. So yeah, good day to all you guys. And I also give the floor back to Agata.
Thank you very much, Katja. And so we encourage you to ask questions or give some comments. You may do that on a chat. Oh, yes, we have a question. Is river ice, sea ice, and glacier all very different? For example, if you have to break frozen river or frozen sea, what are some important things to know?
Okay, thank you very much for the question and for curiosity. I see that river ice, sea ice, and glacier ice, of course, they're different, and there are different aspects that bother us in changes in this ice. For example, with river ice, it's important for northern territories, for example, like for North Eurasia and for North regions of North America. There, for example, river ice serves as a route to travel and to cross rivers during winter, and it has actually quite huge economical meaning in some regions. And in recent times, those river crossing on the river ice are operating for shorter periods. They start breaking earlier, and that actually poses quite a huge threat to economic activities of the local population, because they used to use this kind of river crossing with vehicles and for local population. Then it changes also timing of river floods, and there are also ice jams formed with this breaking ice that serve as natural dam, and there are these ice jam break floods, very intensive ones. So there's a huge spectrum of processes around here. I've studied more rivers than sea ice, so I cannot tell you lots of things about sea ice, but I can as well tell you that there is less ice around the sea in Arctic areas, and those periods when it's formed, it also changes, and it can be studied from space, and there are lots of groups that study these processes. And it also affects how for example, sea transport is operating, sea vessels. So yeah, there are lots of aspects. I even don't know where to start and where to finish, of course. And it would be different from what bothers us with glacier ice, because the glacier ice is first of all water reservoir, while river ice and sea ice, they affect our means of travel and pose threats in terms of flooding and natural dams of this ice that are formed, and then outbreak floods. Thank you for the question.
Thank you for your attendance. Thank you, Katja, for the presentation. And see you next time in different topics and different speakers. Thank you.
Thank you. Have a good day, all of you. Bye.